This is a conclusive video of the practice number 7 of materials behavior class. For this practice I did several tests to a material which is steel 1018. There were 4 types of tests. One of them was tensile strength, another was hardness, another impact, and the last one is the metallographic analysis test. I had to put a piece like this in a universal machine, which is a machine that makes the tensile test. For this part, the machine takes the upper part of this piece and pulls it until it breaks. The results are shown in this table, and as we know, we have to obtain a yield strength, an ultimate strength, and a change in the dimensions of our piece. For this part, I calculated the original diameter and the final one. Same for the area and the length. With these variables, I could calculate the strain of the material, which was 0.17, and the yield strength, which is the strength that this material can take before it has a plastic deformation. And in this case was the yield strength, it was 70,921 psi, and with this stress I calculated the force that generates the stress, which is 14,000 pounds. Also I calculated the tensile strength, which is the maximum force that this material can take, and it was almost 80,000 psi. The force that produces this stress is not that different from the yield strength. The percentage of elongation was 17%, the area reduction was 0.97%, and we have a high elasticity modulus, which means our material is not elastic. Well, for the metallographic test, I had to cut a part of previous piece that I used for tensile strength, and then I put it in backlight, which is this one. After that, it had to go through a process of polishing, and then I made a chemical attack on the material. After that, I had to put the material on a microscope and then use different magnifications to see the grains, which are shown in this picture. This is a magnification of 500x, and I had to count the grains in a square inch of the material. For the magnification of 500, I counted in an area of this picture. I counted 21 grains in total, counting half grains and complete grains. And after the calculation, I got a ASTM size of 10. Well, for the hardness test, there were another 4 tests of one of each type of hardness. The first is Grinnell. It is important to mention that for the 4th test, I used only this piece. Well, for the Grinnell, I got the following results, which are measured diameter of the indentation is 5 millimeters, and the second was 5 millimeters with an average of the same. The result of practical hardness was 143 for all of them, and the theoretical was 142.55, which is very close. For the Rockwell hardness test, I just simply used the other side of the piece and got these results, which are result practical hardness of 40 and 44.5, sorry. And the average was 42.25. Well, for the Vickers test is a microindentation test, which also gives us the hardness. And I got pretty different results for the different tests that I ran. I think it was due to an error of measurement of the diagonals, because as you can see in the results, they are pretty different between them and give us a different hardness and average, which is strange. So I think I didn't measure the diagonals the way they were, and I got bad results. Well, the manual Vickers test was pretty different, well, with not accurate results. For the automatic, I got these results, which are a hardness of 170 and 196 for an average of 183. I think this is the correct because it's the most kind of advanced test, and I don't think that it has the errors due to the measurement. The last test was the impact test, which was pretty fun because I had to smash this thing with a big hammer. Well, pendulum, but it seems like a hammer. Well, for the measurements of my piece that are shown in the table, I got energy absorbed of 29 foot-pound. Well, I think that this energy absorbed is actually low because when I was doing the test, I noticed that the slot of my piece was a little bit too big, and I'm pretty sure that it absorbed less energy than it should.